Hey QED coders, Michael L. Perry here. In the last episode we modeled an ordering system with a customer, their orders, order lines, that sort of thing. And we talked about how we should only insert and never update, never delete records. Now there are some properties that you'd want to put on the customer table, like their name and address, that you'd want to update over time. But we're not going to allow updates, so how are we going to model this? There's a pattern that arises for storing mutable properties in a historical model. Let's go ahead and derive that pattern together. So we've got our customer table, and we're starting out with the customer name and address, and we want to get rid of those from the customer table. Okay, so where did the customer name and address go? Let's talk about the customer name first. So we want to insert in order to change a customer name, so let's create a customer name table. So customer name would have the customer ID, it would have the name, and anytime I want to change the name, I need to insert into this table. Well, what problem do you see here? If we change a customer's name, now we've got two customer name records. How do we know which one is correct? How do we keep track of the current customer name? There are a couple of different ways you might try to do this. We'll go through some of those and then settle on the one that historical modeling leads us to. So the first thing you might try is to add a version number to this table. So every time you create a new customer name, you find the most recent version number, increment it, and then insert with that new version number. And now you can select the customer name with the highest version number. You've got the current customer name. Now you might see a problem with this select and then insert pattern. When you're doing something in high volume, select and insert can cause deadlocks within your application. So that's to be avoided. You can improve this just a little bit by replacing the version number with a timestamp. And so now you're looking for the most recent timestamp of the customer name. Now that still poses a problem when we have multiple nodes and we're trying to capture a customer name from different areas within the application. We're going to avoid the timestamp mechanism, and instead we only want to keep track of the current customer name by the predecessor relationships that it has with other customer name records. Let's see how we can model that. Let's start with this idea for the model, where we've got the previous customer name ID as a foreign key within the customer name table. Now anytime I insert a customer name, I also insert the ID of the previous version of that customer name, and this will create a chain of customer name records, and I can see which one does not have a successor. And so that would be the current version of the customer name. Now there's a couple of things wrong with this. First of all, the initial customer name doesn't have a predecessor, so this column would have to be nullable. The second thing, though, is that if we do capture a customer name change from two different places within the application, we could have two different records that simultaneously replace one customer name with a successor. And so we would have a fork within this tree. If we have a fork within the tree, then we have two potential candidates. How are we going to ever resolve that fork? So a customer name record has to be able to support more than one predecessor in order to resolve this situation. The way that we can do that is by separating that previous customer name ID into a separate table. So we'll call this customer name predecessor. And this is the collection of predecessors for a particular customer name record. And so now within this collection, I've got my customer name ID, and then I've got the previous customer name ID as a foreign key to a different record. And so with this structure, I'm able to capture 0 previous customer name IDs for the first one, 1 for the typical case, or multiple when I need to resolve a fork in the tree back to one single branch. This is how we keep track of mutable properties within a historical model, because it tells us exactly what was the previous version, which versions do not have successors, so I can see what are the current versions. So what does the customer address look like? Well, an address isn't just a single name. It's got the street address, the city, the state, the zip code, several different properties. So rather than have one table for each of those properties, since they all tend to change together, we're going to have one customer address record that has all those properties, and still follows this multiplicity of predecessors concept. So we've got our customer address record, and we've got our customer address predecessors record. So this is how we keep track of mutable properties in a historical model. It helps us to identify and resolve conflicts and keep track of concurrency. So in our next episode, we'll dive into concurrency. We'll compare the historical modeling concept of concurrency to other models, and we'll see how the historical modeling method for managing concurrency solves a lot of really interesting problems for us. So come on back.